Okay. Thank you. So my talk will be on the tidal evolution of circumbinary systems. This morning, Silvio already gave us a nice description of the tidal effects. Just to remind you the most important consequences of tidal evolution, whatever is the model that we are using. Christoph is in front of the slide, but I am telling you. So the main consequences is that the orbital period is synchronized with the rotational period, so that's what we call the synchronous rotation. And there's another consequence that Silvio did not talk about because he was using the planar model, is that in the 3D model, the obliquity of the planet becomes zero. It means that the spin axis becomes normal to the orbital plane. So these are the two main consequences, the classical main consequences, that are valid for anybody undergoing strong tides. So now we'll apply this effect to circumbinary bodies. What are circumbinary bodies? Basically, you put one planet around two stars in an orbit that is circumbinary, going around two stars. There are not many planets so far discovered in this kind of configuration. Actually, I went to Wikipedia yesterday and there are only 21 cases, one is missing in the bottom. So there are only about 20 cases of circumbinary planets already detected. This is the full list. In my talk, I will focus in the yellow ones. The yellow ones were observed by the transit method, so for photometry, for the variation in the brightness of the two stars. Why do I focus in these systems? For two main reasons. One, the most important, is because these systems are completely characterized. It's very impressive that with only photometry, with transits, the people were able to extract the entire orbit. For instance, in this case, in the radial velocity, we don't have the minimum, we don't have the inclination to the line of sight, but with transits, we have everything. The only problem is that maybe these systems are biased, because these systems must be coplanar. Otherwise, we wouldn't observe them. So it raises the question, are all circumbinary planets coplanar? It means, is the orbit of the planet in the same plane as the orbit of the binary stars? Apparently, there is no reason for that. So these guys are, but I don't know, I cannot answer for the other systems that are in white. But there are some observations of circumbinary disks. So we don't observe the planet, but we observe the disk. And for circumbinary disks, a lot of them are not in the same plane of the binary stars. So there is no reason, apparently, that the planets lie in the same plane in the beginning as the orbital plane of the stars, but in this case, they are. The other reason why I choose these systems is because if you look at the semi-major axis of the planet, this is for the planet, you see that it's always smaller than 1 astronomical unit. So it means that the planet is always inside the orbit of the Earth, but more important, if the planet is inside the orbit of the Earth, it means that the binary stars are even more inside. So this is one example for Kepler-16, one of the first systems detected by the transit method. You cannot see very well the orbits in blue. So this is put in context with the solar system. We have here the binary stars. It's a G star and the M dwarf. And this is the orbit of the Earth, 1 AU. So the planet is between, more or less in the same orbit as Venus. And here you have the orbit of Mercury, so the stars are inside the orbit of Mercury. And we know from the solar system that Venus and Mercury undergo strong tidal effects from the Sun. So the rotation of Mercury and Venus is not a primordial rotation, it's evolved. So we can expect that the rotation of the planet is evolved, but it's not important for what I'm going to show. What is important is that the rotation of the stars should be evolved as well. So the stars should evolve to the tidal locule that I showed you before. So another interesting stuff for circumbinary planets is that you see these are the orbital parameters for this system. So if I do the ratio of the semi-major axis, in order for the system to be stable, there is always a small ratio between the semi-major axes. So if I put this to the power to 4, it's less than 1% of error. So it will allow me to perform some approximations in my model. In particular, since this term to the 4th is very small, I will expand the interaction potential, the gravitational potential of interaction between the planet and the binary. I will expand in powers series of the semi-major axis, and I will truncate to this order. So I will do what we call the octupolar approximation. I truncate either order terms So it will allow me to write the equations in an easier way. So the other thing that we are doing is circular evolution. We will average the equations of motion. It means I will average over one orbital period of the planet and of the planet. So I will replace these angles and will disappear. And I will use the vectors, the vector of the total angular momentum, the orbital angular momentum, the g, the spin angular momentum, and the Laplace or the Russian vector to give me the eccentricity, position of the eccentricity. So I lose the information on the position of the planets and the stars on the orbit. But the advantage of doing circular evolution is that tidal effects act in a very long time scale, much longer than the orbital motion. So if I want to put everything together to speed up simulations, it's better to do circular evolution. So this is the model. So we have a three-body octupolar approximation for the gravitational interaction. Also put general relativity corrections because the stars are very close together. We put the spins for all the three bodies and use the linear tidal model for tides. It's the simplest one, but for gaseous planets, as we showed you before, and in stars, we expect to be a very good approximation. So since you like equations in this meeting, I put you all the equations for the three-body interactions, quadrupolar, octupolar, general relativity corrections, spin evolution for all the three bodies, and finally tidal evolution. So these are the types of the equations that we have to integrate, numerically integrate to plot some curves like this. So this is a numerical simulation that uses the previous equations for the motion of the tidal evolution of a circumbinary planet. So I'm showing a lot of information here that we explain a bit slowly. In the first plot, we have the rotational period. So the blue curve is for one of the stars, the zero star, I call it zero, and the other, the largest one, and the smaller one is in red. The same for the obliquity. So this is the rotational period, this is the obliquity. The dotted line is the synchronization line. So I don't know what was the rotation of these stars in the beginning. Actually, I don't think even that we have the rotation of these stars for these systems that were obtained in Kepler. For some of them maybe, but it's the present rotation. I don't know what was the initial rotation. But in order to highlight the dynamical effects that are important in this kind of problem, I put one star rotating faster than the synchronous equilibrium and the other rotating slower. And you see for the obliquity chart that we already have two distinct behaviors. And as I told you before, for tidal effects, usually the rotations become synchronized at the end of the evolution. That's what we observe here. So actually the rotation of the stars becomes synchronized with the orbital motion of the two stars, but the obliquities should go to zero due to tides. And that is not what we are observing here. So it appears that something strange is happening with the obliquity. I will explain later. In this plot, I have the semi-measured axis evolution. So you see it's almost a straight line. So it means that tides may change the rotation of the stars, but they almost do not change the orbits of the stars or of the planet. This is the orbit of the two stars, this is the orbit of the planet. Why? Because we transfer angular momentum from the rotation to the orbit, but there are much more angular momentum in the orbit than in the rotation. So even if you remove a large amount of angular momentum from the rotation, you can change completely the rotation, but you put it in the orbit, and the orbit almost does not change. So this change we cannot see, but there is a slight change. Okay? So we can assume that the orbits are static over time. But when you look at the mutual inclination, so the inclination between the orbital plane of the binary and inclination between the orbital plane of the binary and the orbital plane of the planet, we start with 10 degrees, so there is an oscillation, and then at 7, it goes to 0. But this is not due to tides, at least to direct tides, because direct tides on the orbit have this effect. So this was very surprising for us to observe that when you combine all the circular effects with the tidal evolution, we get a system that it was not coplanar in the beginning, but at the end of the evolution it became coplanar. So what is going on? That's why I will spend the rest of my talk explaining what we are observing here. So we have an obliquity. The system is coupled. The obliquities are coupled with the orbits. That's what we are going to see. So we see the two kinds of obliquity behaviors. In this case, the rotation was increasing, and in this case, the rotation was decreasing. And we see some jumps here. So let's put the simulations in another frame. And the frame that I'm going to choose is the rotation frame of the plane of the star. So in this plot, what I see I only plot for the spin of the largest star. So I take the spin of the largest star, and this is the motion, the projected on the orbital plane of the binary. So this is the obliquity, and this is the mutual inclination, and each color corresponds to the same kind of evolution. And actually, if I forget about the spin of the second star, this problem is integrable. So what I'm showing here is using just the second star as a point mass, and I'm showing the phase space of the system, which is integrable. So, but and the different plots correspond to different rotations of the largest star. So 4.2 days near the synchronization, 4.5, 4.8. And what we observe is that the topology of the phase space completely changes as the rotation of the star changes. And for most of you that are acquainted with resonances, you can see immediately there is a resonance here. So the spin of the star can be either in circulation, depending on the rotation, or in resonance, in libration. And these points that we observe here are very well known in the literature. It's called Cassini states. It corresponds to equilibrium points where the spin is fixed. In the precessing frame, the spin axis is fixed. So remember, for one of the stars, we were increasing the rotation into the synchronous motion. For the other star, we were decreasing the rotation. So that's what we see here. So what happens to the obliquity? So when we are increasing the rotation, so this is the same numerical simulation that I showed you before, but in a different plot. So this is the co-rotation frame, and this is the temporal evolution, and the color gives you the evolution of the time, and so in the two frames. So for one of the stars, we saw there was a jump in the obliquity. So why this is for the star where the rotation rate is increasing. So the rotation rate is increasing, so we are coming from this side to this one. So the rotation rate is increasing. So the phase space is this one, and then it's modified to that one. So what's happening is that initially we are in circulation, we are moving around here, around Cassini state 1, but because of the increase of the rotation, we cross the separatrix of the resonance, and we jump, and then we are in circulation around state 2. So we can also follow from this one. So we are increasing the rotation rate. So we are coming from this side. We are around state 1, then we cross the separatrix, and then we are around state 2, but there is a different obliquity between those two states. That's why we observe a jump. For the other simulation, the rotation of the star is decreasing for larger values. So we are initially around state 2, and then we cross the separatrix. We may either be capturing resonance or not, but the most likely scenario is to be trapped in resonance. So as you see, the obliquity increases because the phase space is modified. So initially we are here, and then we are trapped in resonance, and we continue, and the obliquity is increasing following the Cassini state. So we are here initially in circulation, then we are capturing resonance, the obliquity increases, and then it decreases. Again, this is exactly what we have shown here. Okay? And what about the mutual inclination? The system is so these phase spaces that I showed you before, they are coupled. So the mutual inclination is coupled with the obliquity. When I change the phase space, I change the equilibrium values for the Cassini states that depend on the obliquity, but they also depend on the mutual inclination. And you see that the mutual inclination also changes when we change the obliquity. So the topology of the phase space changes only because the rotation of the star changes. But when the rotation of the star changes, I change the topology, and the mutual inclination changes. So this is what I show here. Where this is the obliquity, so Cassini state 2 is the same curve as in here. And this is the mutual inclination that corresponds to this obliquity. So initially we have almost 10 degrees and a small obliquity. So then, due to the evolution of the rotation rate, we are trapped in resonance. The obliquity increases, but when the obliquity increases, the mutual inclination has to decrease. This is only due to the total conservation of the angular momentum. So this is my result. I go to the conclusions. Jacques is already playing that I have almost over time. So conclusions. Long-term evolution of hierarchical systems can be described by average circular equations of the motion. Circumbinary planets with initial arbitrary orbital inclination can become coplanar through this secular resonance between the precession of the orbit and the precession of the spin of one star. I forgot to say what was the resonance. Sorry. So there is one resonance. This resonance corresponds to the resonance between the precession speed of the spin axis of the star and the precession of the orbit of the planet. Sorry. And this model is very general because we use three-body non-restricted. So as long as we apply to circumbinary planets, but as long as your problem is hierarchical, you can expand the potential up to the octupolar order, and you can apply this problem to this model to circumbinary planets, but it can also be applied to satellite planet star systems or even triple star systems. Thank you.
Thank you for